Hi class, this is Nelson Jones, and this is the Advanced Concepts Presentation 2. We're going to derive the Michaelis-Menten equation. So let's just go ahead and get right into it here. We're going to start with this concept of this equation here and derive out of it the Michaelis-Menten equation. So we're going to kind of start with this general reaction that was given, and just to name our what's in it, we got E is our enzyme, S is our substrate, and then when we have our enzyme and substrate react together, we have enzyme substrate complex, and then the enzyme substrate complex dissociates to form an enzyme and product. So we're going to denote the enzyme and substrate turning into the enzyme substrate complex as K1. So that's this turning into this on the top. That's going to be K1. We're going to denote our enzyme substrate disassociating back into enzyme and substrate as K-1. And then our enzyme substrate disassociating into enzyme as product as K2. So there's our kind of simple equation. And here we're gonna start with our first assumption, and that's called the steady state assumption. And that's that the rate of our formation is this equal to the rate of dissociation. So when we're looking, our rate of formation, that is our enzyme and substrate forming into the enzyme substrate complex. So that is K1 enzyme substrate is going to be equal to our rate of dissociation. So that's going to be K-1, and that's when our enzyme substrate complex is dissociating, times that, plus our K2, and that's going to be also when this is dissociating. So we're also going to have our ES, enzyme substrate complex. And then another thing we need to think about here is our enzyme total. So our enzyme total is equal to our enzyme substrate plus the free enzyme. So it's going to look like enzyme substrate plus our free enzyme. Then what we want to do is we want to solve for just the enzyme here on our enzyme total. So if we take our E, if we subtract it, we'll get E is equal to our enzyme total minus enzyme substrate. Then what we want to do is plug this E equals enzyme total minus enzyme substrate into our equation here on the left, into our steady state assumption. So we're going to go ahead and do that now, which is going to give us K1. We'll do a parentheses, so then we're going to plug in our E here. It's going to be E enzyme total minus enzyme substrate, close our parentheses, times concentration of substrate. And then we'll equal that to our other side of our equation. So we're just going to copy that over. So now that we have this, what we want to do is we're going to multiply our K1 and our S, our substrate concentration, into this parentheses. Then we're also, over here, we have a common factor of our enzyme substrate complex, and we're going to pull that out. So we'll do that at the same time here. So we got K1. Equal to, so now we're going to pull out our enzyme substrate complex. Parentheses, K-1 plus K2. So thinking about this, you can see we've got K1 here on the left, in each equation on the left. And then another equation we're going to think about here is our Michaelis constant. And that is Km is equal to K-1 plus K2 over K1. And that's kind of the rate of dissociation over our rate of formation. So what we want to do is factor out K1 here. So we're going to have K1 times our enzyme total. Then we're just going to copy over the right side of this equation. So now that we just factored out our K1 here, we can divide by K1 on the left. When we do that, K1's going to cancel. And then when we divide over here, we've just formed right here our Michaelis constant. So we're going to plug that into, we'll just rewrite our equation now that we've kind of done it here. So we've got enzyme total, substrate concentration, minus our enzyme substrate complex, substrate concentration. It's going to be equal to, so we've got just our enzyme substrate complex here, and then this whole thing became Km. Then what we want to do is go ahead and add this ES to this side, so we'll rewrite that. Now that we've rewritten that, you can see we have ES here. We can factor that out on the right, and so we'll go ahead and do that. So the left is going to stay the same. Then we'll factor out our ES, enzyme substrate complex. So now we're kind of going to think about, we want our enzyme substrate by itself here. So we want to solve for that because we're going to plug another equation into our ES. That other equation is V naught is equal to K2 times ES. So if we solve for ES, it is equal to V naught over K2. So what we want to do is get ES by itself and divide by, to get ES, our enzyme substrate complex by itself, we just divide by our Km plus X. So it'll give us our enzyme substrate is going to be equal to, so that would cancel. Then we have our enzyme total, our substrate concentration over Km plus S. Oops, sorry, kind of off the page there, I wasn't looking. So now that we've done that, we can plug in ES for that V naught over K2. So we got V naught over K2 is going to be equal to enzyme total, substrate concentration, all over Km plus substrate concentration. So now we want to get V naught by itself. So we'll multiply by K2 over 1. I'm going to kind of do that this way. So we got V naught is going to be equal to K2 enzyme total all over Km plus S. So here we're going to kind of talk about another assumption we're going to make from here, and that's that V max is going to be equal to K2 times enzyme total. And the reason we can make that assumption is that at Vmax, all the enzyme is completely saturated with substrate. So there's no more enzyme available to add substrate. And so that means there's no more free enzyme left. So if we look at this steady state, or this enzyme total assumption up here, if there's no more free enzyme left, say that's gone, then our enzyme total equals our enzyme substrate. So we'll just say Vmax is equal to K2 times your enzyme total. You can see Vmax times is equal to K2 times ET. It's right here in this equation. So what we're going to do is plug that in. So we have V naught is equal to, oops, we're taking that out, is equal to Vmax times substrate all over Km plus substrate. So now that we've plugged that in, this is our Michaelis-Menten equation. So we've taken our general reaction up here, and we've derived our equation, this Michaelis-Menten equation, right here. And this is pretty much foundational to enzyme kinetics. And then one more thing that we want to talk about here is we want to understand this Km a little bit better, the Michaelis constant. And so go ahead and flip it over here. So we can assume that V naught is equal to our Vmax in half, so Vmax over 2. And if we were to plug this into our equation, we could have, to our Michaelis-Menten equation, we would get Vmax over 2 equal to so we want to solve for Km here in this equation. So what we're going to go ahead and do is just cross multiply these. So we'll get 2 Vmax substrate concentration is equal to Vmax times Km plus substrate concentration. So if we divide by our Vmax here, they'll cancel out and we will be left with 2 substrate concentration equal to Km plus substrate concentration. So now we can subtract S, 2 minus 1, our Km is equal to substrate concentration. And that's when we're at 1/2 of our Vmax. So Km kind of tells us, which is our Michaelis constant, tells us the substrate concentration at 1/2 Vmax, and it is also somewhat helps us to learn about the affinity of an enzyme. So here you can imagine if we have a low Km, it's going to have a high substrate affinity. And then if we have a high Km, it's going to have a low substrate affinity. So it tells us how much of a substrate an enzyme can take on. And the low Km here means that it won't take on much substrate, while the high Km means that the enzyme will take on more substrate. So that's understanding a little more about the Michaelis constant. And then here we have our derived equation where we end up at our Michaelis-Menten equation. I hope that was helpful. If anyone has any questions, just give me a shout. Thank you.